All right, so in today's short video, we're going to be talking about states of matter. And the goal for this video, once I get control of my PowerPoint, there we go, is to identify and explain differences among gases, liquids, and solids. Let me get my pen out here. Sorry. In terms of visible properties, distance between the particles, and particle movement. All right, so let's get started. So there's three familiar examples of states of matter, I think that we're all familiar with: solids, liquids, and gases, whether it be, the water we drink, or maybe the chair you're sitting on, or the air you're breathing. Those would be examples of each of these states of matter. And so again, we're familiar with these different states of matter. I think we can identify them by, feeling them or looking at them. But the real question is, how can we explain the differences between these states of matter? And the way that chemists would do that is using something called kinetic molecular theory. Okay, that's how a chemist would explain the differences between solids, liquids, and gases. And according to this theory, what we need to keep in mind is that all matter consists of tiny particles that are in constant motion. All right, so these tiny particles come from the word molecular here in kinetic molecular theory. So you can think of, in our example, or an example we'll get to, excuse me, okay, so that particle would be something like a water molecule that we'll see in a second. And the motion part comes from the kinetic part of kinetic molecular theory, okay? So we have these tiny particles, they're moving around, okay? And we can explain the differences in matter by looking at how they're moving, all right, in part. One thing to keep in mind with kinetic molecular theory, though, is that particles move faster at higher temperatures compared to at lower temperatures, okay? So this is something to keep in mind, okay? It's pretty important. So again, particles that are heated up, they're at higher temperatures, are going to move faster than particles that are at lower temperature. And again, I think that comes probably intuitively for a lot of us. You could think about if you put something in the freezer and things are freezing, it's more of a solid, right? So it's getting colder. The particles, you may not have thought about it that way, but the particles aren't moving as fast. So that's what we're going to talk about. There's also this other key that is, there's also attractions among particles in all states of matter, or all samples of matter, or states of matter. So the particles not only are moving, but they're also attracted to each other. And so if we look at those differences between a solid, liquid, and a gas, it'll help us to explain these differences. So moving on then, the state of any sample then depends on the temperature that it's at and the attraction among the particles. And so at higher temperatures, as the temperature is raised, so let's imagine with me here that we put a beaker on a hot plate or on your stove, okay, and it has a small amount of water here at the bottom. These guys here are water molecules. So I'll just say H2O. Oh, sorry. There we go. So these are H2O water molecules. Remember from our last video, kind of the representation of them. So this is showing the kind of the structure of these water molecules. And as the temperature of the sample is raised, these water molecules, or these particles, separate from each other. Okay, so as they separate from each other, they go into the gaseous state. Okay, they're in the gas state. And when they're in the gas state, these particles move fairly quickly. Okay, they move fast. So they're kind of zipping by each other. And they also fill the volume of the container that they're in. So you could think about it, these gas molecules are just flying around wherever, like air in a room. So they fill the volume of whatever they're in. Okay, so whatever container that we have or we're putting these water molecules in, they'll fill the volume of that container. So again, this is in the gaseous state. So there's, again, attractions between all particles in all these states, right? So in all samples of matter, there's attractions between the particles. But in the gas state, the attractions have no effect because the particles are moving so fast. And they're fairly far away from each other too. But so you could think about it this way, there would be an attraction between these particles, but they're zipping by each other. They're moving so fast, there's not enough time for this attraction to be felt. Okay, so that's in the gas state. So these particles, so one last thing about the gas state, they need to be kept in a closed container, okay, or they will escape, right? So in this case, they're just escaping. But if we wanted to keep them, obviously, again, we need to put a lid on this container and seal it up, because they're just going to fill the volume of whatever container or whatever room they're in, okay? So let me just write one thing that I said. So this is low attraction, okay, between the particles. So between the molecules. Okay, they're far apart from each other. They're not feeling an attraction. All right, so that's in the gaseous state. Now, if the temperature decreases, okay, so we now turn off the burner, turn off the hot plate, we're cooling this thing down. As the temperature decreases, the particles also slow down. Okay, so as the temperature decreases, the particles slow down. And so because they're slowing down now, the attraction between the particles has more of an effect. So you could think about it this way. The particles then, because they're being attracted to each other, they begin to clump together and you begin to form a liquid drop. Okay, and that liquid drop falls to the bottom of the beaker here and you get more and more drops. Oh, excuse me. And now you have water, okay, as we would know it, okay, liquid water that is in this beaker. Now, there's a few things to keep in mind here. The first is that the volume of this liquid is constant. Okay, so I'm going to write that down. So the volume of okay, so the volume of the liquid is constant. It might change with temperature a little bit, but for our purposes, we're just going to say that the volume of the liquid is a constant. Okay, so that's something to keep in mind. It, of course, is going to take the shape of the container it's in, but the volume of the liquid is constant. Now, we decrease this further, all right? We throw this in the fridge. We want to make some ice cubes. And so as the temperature decreases further, the particles become even more sluggish, okay, until they no longer move freely, okay? So now, right, they become more sluggish, like I said, they no longer can move freely, and this is the solid state, okay? So you formed an ice cube. So they begin to arrange themselves in repeating patterns. They're frozen, okay? And like the liquid state, all right, the volume is also fixed, okay? The volume is also constant. Of course, in this case, though, it doesn't take the shape of the container. I'm just going to fix that O there, or I'm going to attempt to fix that O. There we go. It doesn't take the shape of the container, though, because it's an ice cube, okay? So it's going to, you know, if you made an ice cube in the fridge and then you put it in your glass, obviously it's not going to take the shape of the glass. So that's what we're talking about here, that the volume is constant and it has a constant shape, okay? And the shape doesn't change in the solid state. So that's all for this lecture on states of matter. So next time, I believe we're going to be talking about physical and chemical properties and changes.